All right, here we go. Chapter 2. We start off by trying to figure out when we've got a set of numbers that's related to another set of numbers, making it a relation, is actually a function. So we've got different ways to show relation. Here I've got 4 different ways to show a relation. We could write them as ordered pairs, which I think we're pretty much used to. We've got an x that goes to a y, an input that goes to an output. So based on this, hopefully you look at each of the first 3 things here, you're seeing that you've got an input as being basically in the x position. Here I got input, and over here I got input with x. In the middle, it's the same thing. I'd have my x's going to my y's. So the one thing you have to look for is if you've got the same exact x going to different y's. If I gave you a problem and I said plug in x, you should get one answer if you follow the order of operations. Like if I said, okay, solve or evaluate x squared minus 3x plus 2 when x equals 5, there's one thing you get. You plug in 5 and you'd end up getting 12 because 25 minus 15 is 10 plus 2 is 12. But everybody should get 12. When you plug in the same x, if somebody plugged in 5 and came up with something other than 12, and they were right, that would not be a function. So when you plug in a number, in this case we plug in 5, no matter who does it, as long as they do it right, they should get 12. It should go to 12. So where there's situations where a number goes to different, an input goes to different outputs, here's one right here. I've got 2 4s, and one of them gets you a -1, the other one gets you a 3. Another way to show that was a mapping diagram where they've got the 4 and they've got the arrows coming right out of there. Here's my 4, and the arrows, I got 2 arrows coming out of one spot going to 2 different spots. Then it's not a function. This is basically over here, just the same thing as what I had for ordered pairs over here. Just kind of neatens it up a little bit, doesn't have the parentheses. And then the last way to graph, you can tell if something's not a function if you've got points that lie on the same vertical line. So here I've got 4, -1, here I've got 4, 3. They lie on the same vertical line, so that tells me right there that it can't be a function because I've got 4 going to 2 different spots. So that's the basics of when a relation is a function. So is the above relation a function? Well, I went over why it wasn't. I've got 2 4s that go to 2 different numbers. I've got the same 4 that is listed twice, and it's going to 2 different numbers. So is the above relation a function? No. 4 could go to -1, or 4 could go to 3, and that's what can't happen. Now you could have it the other way. You could have you could get the same y and be a function. I could plug in different x's and get the same y, and then it's still a function. So be careful here. Don't get confused if I were to turn around and say, oh, what if I had -2 is 4 and 2 is 4? You might be thinking, oh, I got the same, but there's different numbers. Actually, this is okay. It's okay to plug in 2 different x's, but get the same y. That's okay. One thing not okay, 2 same x's going to different y's. So, the domain, talking domain and range. The domain is all your inputs, so domain is all your x's. Range is all your outputs, so range is all your y's. So if I ask for domain and range, it's simply list the x's for the domain, list the y's for the range. I already mentioned this, a way to determine if a relation is a function is the vertical line test. Again, you've got a graph, you draw a vertical line and it hits more than one point, not a function. So let's look at some examples. Write the following ordered pairs as a mapping diagram and graph them on a coordinate plane to determine whether or not they represent a function. List the domain and range. Well, my mapping diagram has me listing my x's, which are 4, 3, 5, and 2. You can put them in order, out of order, I don't really care. I guess I'll put them in order here. So 4, 3, 5, 2 would actually be 2, 3, 4, 5. those numbers represent my input, they represent my x's, but more importantly, they represent my domain. And if I ask for a domain, I'd use this funny little bracket here, and then I'd put the numbers that are in the domain in the brackets. The output are the y's. I'm doing a mapping diagram, so I can put those in order as well. My y's, I'll use a different color. I've got 3, -2, -2, and 2. So it's -2, 2, and 3. I don't need to write the -2 twice. Now I listed my output. Those are my y's. More importantly, though, they represent my range. So my range is -2, 2, and 3. The mapping diagram says, what does 2 go to? Well, when x was 2, it went to y is 3. So it's drawn over there. When x was 3, it went to y is -2. When x was 4, y was 2. And when x is 5, it also went to -2. There's your mapping diagram. The graph, 4, 2, graph the first point, 4, 2, that's 4 right, 2 up. On the second point, it's 3 right, 2 down. Third point's 5 right, 2 down. And then finally we got 2 right, 3 up. Is this a function? Yes, it is a function. There aren't any of the same x going to different y's. I can't draw any vertical line that goes through more than one point. Here my line goes through point 2, 3, nothing else. Here my line goes through the point 3, -2, nothing else. 4, 2, nothing else. And then finally the 5. And I should have went down a little further on that point. Not real calibrated here. So this other point here, let me erase that. Should be down to 5, -2. Should have been down to -2. So hopefully you notice I missed that, and you caught it before me, but now you're okay with me catching it myself. Okay, so there weren't any vertical lines. This vertical line only hit one point at any one given time. I did have one other point erased. That was 3, -2. That was right here. I can't remember if I had that in the right spot or not. I might have been one off on that one as well. I'll have to review to see. Okay, does relation pass the vertical line test, which would make it a function? That's what I'm discussing already up above. It did not pass, or it did pass it. Did pass. So it's a function. Again, no vertical line hit more than one point. I was only able to hit one point at a time. Over here. Okay, so for some reason, I see my shapes didn't all show up. I got erased. I think I must have erased some writing, so I'm going to have to kind of redraw these in. The A was like this, C was like this, and what it comes down to is there any vertical line that hits more than one point? So I just got my vertical line right here. As I go from left to right, do I ever hit more than one point? On this first one, my goal was to say no. I mean, somebody might argue, oh, that looks like it's more than one point. I was trying to make it so that I always progress from left to right. So I did not want to hit more than one point anywhere on A. Can I hit more than one point on B? Certainly. B hits a point here, and it hits a point here. That's hitting C twice, my graph of C, so that right there is not a function. How about over here? Here as I go left to right. Again, the idea is I'm progressing left to right. I'm never hitting more than one point, so that one should be a function. So here we had a function. Here, no function, not a function. And over here we had a function again. Y equals 5x plus 3 is an example of a function rule. Which letter would you consider to be the input? So if I told you to plug in, what would you plug into? Well, hopefully it'd say I'd like to plug into x, because if I can plug into x, I can get y really easily. The input letter is called the independent variable. But here we plug into x. That makes x our independent variable. That's doing what it wants. It's independent. The output letter, which would be y, is the dependent variable. It depends on what we plug in. You get y depending on what you plugged in for x. So that's independent, dependent. What output would you get for an input of 2? Well, that's just telling you that let x be 2. Follow the order of operations, and you should get 13. Another fancy way to write y equals 5x plus 3 is f of x equals 5x plus 3. F of x simply means y. So when you see that, don't think of f of x meaning f times x. It means you're plugging an x into this function. So down here, people think this means 2 times f, but that's not what it means. It means plug in x is 2. So you just take f of x equals 4 minus 3x and let x be equal to 2. So if I said find f of 2, that just means plug in 2. 3 times 2 is 6. 4 minus 6, negative 2. That's the answer. It doesn't mean 2f. You don't divide by 2. That is the answer. It just means plug in. F of negative 1 means plug in a negative 1. So I'm taking 4 minus 3x and I'm plugging in negative 1. Minus 3 times negative 1 is plus 3. 4 plus 3 is 7. That's it. The fact that it looked like f of negative 1 doesn't tell you to do any more math. It just means plug in negative 1, simplify, you've got your answer. So this last one, plug in 10. What would you get? Give you a second. Hopefully you're thinking I plug in 10 and get 30. 4 minus 30, excuse me. I have to write 4 minus 3 times 10 is 4 minus 30, and that'll get you negative 26, and that's all there is to it. Finally, I added one problem here. There will be a problem like this, problems like this in your assignment. And again, I think I've got one of these on your test, where you have to look at a graph and determine domain and range. Again, domain stands for your x's. So if I asked you what x's could you have on this graph over here, and I'm going to put arrows on here to show that this goes forever and ever, you should say that this graph only goes so far left. How far left does it go? X's are left and right, right? So when I talk x's, I want to think how far left and how far right does it go? This graph only goes left that far. What's the x value right there? Negative 2. It continues to go to the right, and so x gets bigger. X could be negative 1.5. It could be negative 1. It could be 0. It could be 1. It could be anything to the right of there. So it goes left as far as negative 2, but it goes forever right. A way to write that would simply be x's could be greater than or equal to negative 2. That's what the domain is. Range, on the other hand, is your y's. So looking at this graph, you want to think y goes up and down. How far up and down does this go? Well, because I put this arrow on here, this thing goes forever down. It's not going down very fast, but it's going forever down. It's going forever right as well, but we already took care of that with domain. For y's, we're interested in up and down. It's going forever down, and here it's going forever up. So for y's, it could be anything. It could be all real numbers. A quicker way, a neater way to write all real numbers is this symbol. It means the same thing. I'm going to write an 11 and then turn it into an R. So it looks like kind of a super R. I call it double bar R. That means all real numbers. That's it for our lesson on functions, whether or not a relation is a function or not, and domain range. Have a great day.